On a warm summer evening back in 1985, just a few minutes after departing Tokyo, something unthinkable happened on board a Boeing 747 as it climbed towards its cruise altitude. This would eventually become the deadliest single aircraft accident in aviation history, and also produce one of the most exhaustive investigation reports ever written. And yet, despite the depth of that investigation, it would still remain an event surrounded by misunderstandings, incomplete explanations, and persistent misinformation. And that is why we have now decided to tell you this story. You see, the story of Japan Airlines Flight 123 was not just a devastating tragedy. It would also become the kind of turning point that forced the aviation industry to finally reconsider long-standing assumptions about how aircraft repairs were inspected and documented. But to really understand why that was the case, we have to start long before anything actually went wrong. In the early evening of August 12, 1985, the Boeing 747 involved in this story was preparing for an otherwise routine domestic flight from Tokyo Haneda to Osaka. The whole turnaround had proceeded without any issues at all, with no mechanical snags reported that day. The aircraft, registered as JA-8119, had been delivered brand new to Japan Airlines back in 1974. By the summer of 1985, it had accumulated over 25,000 flight hours and more than 18,000 pressurization cycles, figures reflecting a long and busy service life, carrying passengers across Japan's domestic network. Now, although the aircraft had been delivered 11 years earlier, age alone doesn't really work as a meaningful indicator of safety. Large transport category airplanes are designed to withstand decades of continuous operation as long as they are maintained properly. But this particular aircraft carried something in its structural history that made it different from almost every other 747 flying that day. 7 years earlier, in 1978, this same airframe had suffered a tail strike while landing at Osaka, fracturing the aft pressure bulkhead, the dome-shaped structure that seals the pressurized cabin from the unpressurized tail section. Following that incident, Boeing technicians were dispatched to carry out the repair. And it is here, within that repair, that the entire tragedy would eventually be traced back to. The correct procedure called for a continuous doubler plate riveted across the fracture using 2 full rows of rivets, spreading the cyclical stress of pressurization evenly across the joint. But during the repair, technicians instead used a single row of rivets through a plate split into 2 separate pieces, joined at a seam that ran directly through the load path. This left the bulkhead with roughly 70% of its designed fatigue strength, an error that would go unnoticed for the next 7 years. Hidden behind insulation blankets in a part of the aircraft nobody would ever have reason to inspect closely again. Now, this is worth pausing on. This wasn't a single dramatic failure. It was a quiet miscalculation, buried inside a structure that looked, from every visible angle, completely normal. And every single pressurization cycle after that repair, every takeoff and landing, placed additional cyclical stress directly onto that compromised seam, slowly growing a fatigue crack that nobody could see and nobody was looking for. And this is also where the design philosophy of the era becomes important to understand. Boeing's 4 hydraulic system architecture on the 747 had been engineered with such extreme redundancy that a total loss of all 4 systems simultaneously was considered, at the time, to be effectively impossible, a combination of failures so statistically remote that it fell outside the scope of realistic emergency planning. Pilots trained for single or even double hydraulic failures, but never for a scenario in which every hydraulic line was severed at once. So, whatever eventually threatened this aircraft would have to defeat not just one safety margin, but the entire logic behind why that redundancy was ever considered sufficient in the first place. Anyway, as the aircraft pushed back from the gate at Haneda on the evening of August 12th, it carried 509 passengers and 15 crew members, making this one of the busiest domestic flights of the peak summer travel season, just before Japan's Obon holiday. The crew that evening was highly experienced, led by a captain with more than 12,000 total flight hours. Nothing about the preparation, the weather, or the dispatch stood out as different from the thousands of other turnarounds this aircraft had completed in its career. At 1812 local time, The 747 lifted off from runway 15 and began its climb, banking towards its cruising altitude for the short hop to Osaka. The climb continued normally for 12 minutes, with the cockpit voice recorder capturing nothing but routine chatter between the pilots. And then, at 24,000 feet, the fatigue crack running silently through that flawed repair finally reached its limit. But the full significance of what happened in the next few seconds is only really understandable once you know exactly what that ruptured bulkhead was sitting directly in front of, and why 4 remarkable people in the back of that cabin would still be alive to tell investigators what those final 32 minutes actually felt like. The aft pressure bulkhead ruptured violently. The pressurized cabin air, suddenly finding an opening into the unpressurized tail section, rushed backward with tremendous force, and that shockwave tore through the base of the vertical stabilizer, ripping most of it away from the aircraft in an instant. Because the vertical stabilizer housed the hydraulic lines for all 4 of the aircraft's independent systems, all of them were severed within seconds. In a design considered virtually impossible to fail completely, the crew now had 0 hydraulic pressure, and with it, zero conventional control over the elevators, rudder, and ailerons. What followed was 32 minutes of the crew fighting an aircraft that could no longer be steered through any normal control surface, using only differential engine thrust to nudge the nose left, right, up, and down. Cockpit recordings captured the crew methodically working through emergency checklists, adjusting throttles by hand to control an airplane that aviation engineers had never designed anyone to fly this way. The aircraft entered a series of long, rolling oscillations, climbing and diving as the crew fought for any semblance of control, all while descending gradually across the mountains northwest of Tokyo. At 1856, after that extraordinary half hour, the aircraft struck a ridge near Mount Takamagahara in Gunma Prefecture, breaking apart on impact. Of the 524 people on board, 520 were killed. Remarkably, 4 passengers, seated together in the rear of the cabin, survived. Now, what followed this tragedy was an investigation of extraordinary scale, carried out by Japan's Aircraft Accident Investigation Commission, working alongside the National Transportation Safety Board and Boeing. Recovery teams worked for months across the mountainous crash site, reconstructing sections of the fuselage in a hangar to trace exactly how the rupture had begun and propagated. Fracture surfaces on the aft bulkhead were examined under laboratory conditions, revealing beach marks, the telltale striations left behind by slow fatigue, crack growth over thousands of pressurization cycles, radiating outward from the improperly repaired seam. And it is really important to note that the confusion surrounding this accident didn't end with the investigation. For decades afterward, a persistent theory circulated, and still circulates today in parts of Japan, that the aircraft had actually been struck by a missile fired by a Japan Air Self-Defense Force fighter jet during a training exercise, and that the government covered up the real cause. Some witnesses on the ground reported seeing an orange object near the tail before the rupture, but investigators found no physical evidence of any external explosive or projectile impact anywhere on the recovered wreckage. No shrapnel peppering, no blast fragmentation patterns, and no high explosive residue on any component. Instead, every piece of physical evidence, the fatigue striations, the rivet pattern mismatch, and the direction of metal deformation around the bulkhead, pointed to one single mechanical origin, a repair done wrong 7 years earlier, slowly failing under the ordinary stress of routine flight. So, together, all of the physical evidence eventually eliminated the possibility of an external strike, not through assumption, but through mechanics. The orange glow witnesses described was almost certainly the sun reflecting off the aircraft's polished metal fuselage during its final descent. The lasting importance of Flight 123 doesn't come from how the investigators reached their conclusions, but instead in how the aviation industry learned from it. This accident fundamentally altered how structural repairs were documented, inspected, and signed off across the entire industry. In response, Boeing and regulators worldwide introduced far stricter repair oversight procedures, requiring detailed engineering approval and independent verification for any repair touching a pressure vessel structure. Airlines also implemented supplementary inspection programs specifically targeting previously repaired areas, treating any prior repair as a location demanding lifelong extra scrutiny. So, this accident didn't reveal a single hidden defect in aircraft design. It revealed how a single undocumented shortcut, made under time pressure during a routine repair, could lie completely dormant for 7 years before catastrophically resurfacing. Japan Airlines Flight 123 remains a profoundly tragic event, but it also stands as a stark example of how aviation learns from relentless examination of every failure, no matter how long ago its true cause was buried. Over on our sister channel, Mentor Now, we actually did a video about how modern aircraft achieve hydraulic and flight control redundancy through backup fly-by-wire systems, much of which can be traced directly back to lessons learned from this exact accident. Please make sure that you have subscribed to both of our channels if you want to see more content like this, and if you want to get more deep-diving industry explanations connected to it. Have an absolutely fantastic day, and I'll see you next time. Bye-bye.